Then the next talk, dear audience, is from Barry Duggan from the United States, Kilo Victor 4 Foxtrot Victor. And it's a GNU Radio topic also. It's about understanding ZMQ blocks. And let me introduce Barry to you very shortly. Barry is a graduate of Georgia Tech in electrical engineering and is a career computer programmer specializing in real-time control and data communication systems. He has been an amateur radio operator since 1953 and now devotes most of his time to the GNU Radio project. And he's a member of the GNU Radio General Assembly and he's currently the documentation lead in GNU Radio. So, Barry, thanks for coming in. And we've also pre-recorded your contribution. And for the video team, please, let's start with the talk.
Hi, I'm Barry Duggan. I've been an amateur radio operator since 1953. My call sign is KV4FV. I'm a graduate of Georgia Tech in electrical engineering. I've been computer programming since 1962, and I've been involved in GNU Radio about 2 years and primarily work on documentation. So today I'd like to do a presentation on understanding ZMQ blocks and have the outline here, and this will also be posted on a web page later. So we're going to talk about the types of blocks, the addressing, applications in flow graphs, and then some terminal functions. So first of all, we have some excellent tutorials in the GNU Radio Wiki, and I recommend them highly. And the one we're doing today is the Understanding ZMQ Blocks. There are, let me get back to the top here. Yeah. There are two basic groupings of the ZMQ blocks. The data blocks are ones that handle streaming data, and the message blocks handle messages in PMT, polymorphic types coding. Within those blocks, there are three different pairs that communicate with each other: a pub sub, a push pull, and a request reply. The pub sub can be compared to broadcasting, where the publish sync sends out data which can be received by multiple subscribers. The push-pull is a peer-to-peer type arrangement of equal peers. The request-reply is also point-to-point, but it has a restriction of being totally in lockstep. One request requires one reply before it can send out another request. So using those blocks, I'm going to show how they can be used in various types of data and messaging configurations. The first one's going to be with a ZMQ pub sync. So let me go to the wiki page for that and look at the addressing. The format of the address is TCP, an IP address, and a port address. So for a local host, we use 127.0.0.1 for the local host. And if both of the ends of the sync and source are on the same computer, localhost is faster than using a full IP address. But if we have it on two different computers, then we have to use the full IP address of the sync. And I'll get back to that in a few minutes. So the first example here, go back to the tutorial. First example is actually taken from another tutorial called Simulation of an AM Transmitter and Receiver. So the transmitter section takes audio, adds a constant, which creates the carrier, multiplies that times a carrier signal, because we're simulating a transmitter, and pump that into a pub sync. The addressing on the pub sync is the local host and a port number of 50,001. So on the receive side, we have a sub source with the same local host and port of 50,001. So that signal then is received. The 48 kilohertz carrier is shifted down to baseband, and then it's demodulated. So my main point here is that the pub and the sub have to have the same addressing, same port number, and if they're on the same computer, then use the local host. So now let's look at putting it on two different computers. Now that other was data path. This is going to be message blocks. So I'm simulating a message from a message strobe with a random delay and putting that into a push message sync. Here I'm using the full IP address. So in this example, the sync is at 192.168.194 with a port number of 50,241. So that's what's here. Now to get the pull message source to receive that, we have to use the IP address and port number of the sync. So even though this is on a different computer, in this case it was on 192.168.185, but it really doesn't matter because you always use the IP address and port number of the sync you're connecting to. So here the message source is put into a message debug block, so it will print out the test message on the console. The next example is using a Python program as a request reply server. And Python has import PMT and an import ZMQ, which makes it easy to set everything up. So to create a request socket, I have it broken down here, rather verbose, but it's easy to show as an example. So I build the address and then create a context and then create a socket and then do a connect, because this is a request socket. You do a connect, the reply socket is the sync, and you do a bind on it. The binds are always on the sync blocks. So I set up a reply socket, same way, but a different port number. Create a context, create a socket, and then do a bind on that reply socket. And then drop into a while loop. Now this is a blocking receive. So I sit here waiting for data to come in. And when it does come in, I take that data and deserialize the string with PMT and then convert that PMT into Python string, and that's my message. Now the purpose of this particular Python program is to take the input message and capitalize it and send it back. So I'm going to go uppercase and then take that output and go this same thing backwards. Do convert to PMT and then convert to serialized string and then send it out. Now the example, this next example is probably the most used approach for actually taking data from a flow graph and then processing it in a Python program. So simple flow graph, just signal source throttle into a publish sync. And to show a different approach on the IP addressing, you can publish to asterisk, which says broadcast to all ports, or all interfaces, I should say, on port number 55555. And then the Python program will do a subscribe to that. So we have the import GMQ. Since this is data instead of a message, we're going to use NumPy and time and matplotlib. So we create a context, create a socket, do a connect. And now the one unusual thing for subscribing, you have to set a subject for what you want to subscribe to. So if you subscribe to null, then you get everything that's broadcast. And notice the coding style is different here. Mark Lightman did this one. And so he's doing a test of the socket to see if there's data. And then if there is, he does a receive. And if there's not, he just waits for another 100 milliseconds. So the data, he uses NumPy from the buffer, and it was complex data, so you have to set the data type to complex, and a count of -1 says get it all. So you can print it, print the first 10 values, or you can uncomment these 3 statements and actually plot the data. So that is the, like I say, the most common of the applications. Now there's one more I want to show you, and it's very similar to what you saw a while ago. This is a program that we'll be using in a few minutes with a demo, and it's a push-pull server that capitalizes. So it's just like the request reply that capitalized, except using push-pull. So, and this is one I wrote again, so it's got the same, basically the same commands. Capitalizes and sends it back out. So we've talked about these first 3 sections. Next, I'm going to talk about the attaching a terminal to a flow graph. And there are various ways of doing it, and some work out better than others. The most common, or at least first attempt, is to use standard in and standard out, but they really don't work very well if you have run into blocking issues or various other things like that. So another approach is to use a GUI message edit box for the input, But there are two disadvantages of that. And one is there's no history of what you've typed. And another is after you hit the enter key, the message edit box does not clear. So you have to manually delete what you keyed in before you key in something else. Now here's an example where I used a Python program to send a clear message back to the message edit box. And this is another project I wrote, the Morse code generator. So you type in a line of code, this creates Morse code from it, but also sends a clear message back to the message edit box. Another approach for output, there is a GR display out of tree module that provides a Qt text sync, which is like a screen, but it has no keyboard input, and it is pretty limited in what you can do with it. Well, I was working on a radio teletype project, and I wanted a complete full duplex terminal screen. So I said, well, I'll just write one using Node.js and JavaScript. So let's look at what I need to do for that. The JavaScript does not have PMT functions, nor does it have ZMQ functions. So I wrote my own. So here in the code is a PMT to string function, and it's not too difficult. And then here is a string to PMT function, which is even simpler. And back to my outline here, I actually give line numbers in this on those two functions, and where it sets up the sockets, and where the input actually gets created into an input line and sent. So now let me show you how this all plays together. I already have the example running in the web server. It's the ZMQ push-pull echo, and it's listening on 251 and sending out on 252. And that's all it prints. It doesn't show the messages traffic. So now let me start the create another window here. I have some canned commands. Here. So I'm starting the web server, and I'm starting index.js. So here's my screen. Whatever I type here on the input is going to be displayed below with a greater than sign, and anything I receive on the other socket is going to be displayed below here with a less than sign. So if I type something in here, notice it comes, there's my output, and it came back in all caps because that's what that echo server is doing for me. So if I take some other line here, copy that and paste it, comes back in all caps. So using this with my radio teletype system, I can send radio teletype lines, and then whatever the other station sends back to me gets echoed below. So that works out really well. So it's using 2 ZMQ blocks written in JavaScript. Okay, that is the end of my presentation, and I'm open to questions.
Okay, Barry, thank you very much for this interesting talk on ZMQ blocks. In the background, we've been talking a little about questions that Jean-Michel and Leonardo would raise, but let me very quickly read another question from the chat here. Bob says, could you explain blocking issues with console standard input-output? How could we set up a simple gateway between an asynchronous serial line and a GNU Radio receiver transmitter using ZMQ blocks?
Are you talking about text messages or data? I guess you're talking text messages. Yeah.
Oh yeah. Well, I don't know. That's not a piece of information that's in the chat here.
Okay. Yeah, he just said yes. You can use the GR web server as the. Okay, I'm hearing echoes here. Let me try that again. Okay, you could use the GR web server as your input for but it's not totally asynchronous. It's not, if you mean every time you hit a key, it sends that character out, because it's doing a line at a time. But if you wanted to go in and modify the code there, you could send a character at a time. Hadn't really thought about that much, but I think that would be fairly easy to do. Were there any other questions?
Leonardo, Jean-Michel, who wanted to ask this question?
Well, actually, maybe I can just complement Barry's comment, because on his web server, he's using the push-pull 0MQ, which is equivalent to TCP, which is a connected connection. And maybe answering the question on the chat, if you use the publish subscribe, you will have a UDP-like link where you will just send data out on the network. If there is a receiver, then fine, you will process the data, and if there is no receiver, you will just continue your flowchart. And actually, the 0MQ publish subscribe is something I use very often for radar, where you have a very high bandwidth and you just want to grab packets of data and not the full stream of data. So that's a way I found to asynchronously process some of the data collected by GNU Radio and stream them to some external asynchronous software. But I wanted to ask Barry about how, so he mentioned in his presentation how 0MQ allows him to distribute processing power amongst multiple computers and processing systems. I wanted just him to comment on the fact that 0MQ, how would you maybe use it to interact with different languages that support 0MQ, maybe other languages being more suitable for a given processing than another?
I'm switching between the streaming and the vMix, and it's confusing. When I distribute between several computers, like for the radio teletype, I have one running in Raspberry Pi, another one in another computer, and then frequently the web server interface on the third computer. So, of course, the web server is in Node.js. The others can either be new radio flow graphs or something written in another language, such as Python or C++ or whatever else works out for the application. The Python has a ZMQ library, and I'm sure the others do too. So it should be a simple translation between what I showed in Python and what you would need in the other languages.
Thank you. Yes.
Like
Do we
I
have
say,
any
I'm
more
switching.
questions?
Yeah, I can ask a question if we still have some time.
Yeah.
Is it okay?
Go ahead.
Okay,
Yes,
great.
very briefly.
Yes, okay, very briefly. Barry, very interesting work. I am actually interested in knowing what are the limitations of ZMQ with respect to real-time processing. So I understand that ZMQ is transmitted over a network, and is that going to create any problems with, with real-time processing, and what kind of hardware limitations will create software limitations in terms of real-time processing with ZMQ?
I haven't done any real real-time measurements, but as far as flow in one direction, like flow graph feeding a Python program or whatever, you get a stream and works pretty quickly. But as far as having a interaction where you need feedback from a separate process, we're talking in the millisecond range, but I haven't done any real measurements on exactly how much delay there is. I've done a lot of real-time work in supervisory control and various projects I've worked on, but even then, 10 milliseconds or so was certainly tolerable for those applications. I'm not sure if you would need something quicker than that for what you had in mind.
Maybe yes, but thank you anyway. We can probably continue, and then we'll have other questions.
Okay, thank you very much. Barry, we're going to start with another talk, and we're going to see again later in the group meeting. And our next, well, we're going to see again in the panel anyway.
Right.
First the panel, then the group meeting.
I might comment that this is my first experience with this format, so a little bit confused by what's where.
Well, yeah, that's perfectly fine. Yeah,
Anyway,
distributed conferences. Yeah, distributed conferences are always a little challenging because we have to toggle between different inputs and different topics and whatever. But I think it's going quite well. I'm very content with the way we're producing the stream here. Okay.